So let's see how we find a tangent plane and then use that for helping us deal with some three-dimensional surfaces. And we've been using this equation for finding a plane when we knew a direction, ABC, and then a point, x0, y0, and z0. So we've got a point, and then the normal to the plane given by the vector a comma b comma c. Now we're going to change this equation up a little bit. So we will solve for the z minus z0. So you can see we have subtracted these terms from both sides. So got it over on the right hand side. We're going to divide through by the c, and then we're going to rename these quantities. So the negative a over c and negative b over c we will simply call by the single letters lowercase a and lowercase b. So we end up with an equation that looks like this. So now taking that equation and the equation here of a vertical plane through that point, we're going to set y equal to y0. So as you can see, if we set y equal to y0, then that's going to become a 0. And we're going to end up with the intersection, which is this. Solving for a, we end up with z minus z0 over x minus x0. Now, if you look at that expression, you should recognize that from way back in Calculus 1. The slope of a line, y2 minus y1 over x2 minus x1. This is nothing more than the slope of the function in the x direction. We call that the partial with respect to x. And likewise, if we take the plane x equals x0, that's going to make x minus x0 equal to 0, which is going to give us b equal to z minus z0 over y minus y0. And again, if you look at this, this is our y2 minus y1 over x2 minus x1. This is the slope of a line. That's a derivative. In fact, it's the derivative of z with respect to y. So we end up with that quantity b that we were looking at earlier is nothing more than the partial derivative with respect to y. That means we can rewrite our equation using those quantities of a and b that we just found. Then our equation of a tangent plane looks like this. So notice what is in the position of our direction components is nothing more than the partial of x and the partial of y. So that's kind of replacing our direction numbers. Now again, that's in terms of z. So let's try this out. We're going to find the equation of the tangent plane at the point. Now I'll show you the graph of it in a little while. However, we start by doing the partial of x. So the partial of 2x squared would be 4x. The derivative of negative 3xy with respect to x would be just negative 3y. The derivative of 8y squared would be 0. The derivative of 2x would be the 2. Derivative of 4y would be 0. Derivative of 4 would be 0. So there's our partial of f with respect to x. We need to substitute the point 2, -1 in place of x and y. So that's our partial with respect to x at the point 2, -1. Let's do the same thing with y. Here's the partial with respect to y. We plug in the values. We use our formula for the equation of a tangent plane. Now, the 34 that you see here is nothing more than the z value. So z naught is 34. So we plug all of those in, and here's our equation of the tangent plane. And we can simplify that. Now here you see a picture of the surface. Z equals 2x squared minus 3xy plus 8y squared plus 2x minus 4y plus 4. And the point 2, -1, comma 34. And the plane z equals 13x minus 26y minus 18. And you can see that is indeed a tangent plane. Now, just like in Calculus 1, as long as we are sufficiently close to the point 2, -1, we should be able to use the equation of the tangent plane as an approximation for the surface. They are to be pretty close, as long as we're close to the point. So this is called a linear approximation or tangent plane approximation. We simply take our equation of our tangent plane, plug in the x and the y, and evaluate it. And so that is our linear approximation for f of 2.1 and -1.1. And again, we could have plugged a 2.1 and -1.1 into the equation of the surface. Just would have taken longer. Now, just to clear up some symbolism, here we're saying z is a function of x and y, capital F for our function. So we're making a distinction there, capital F, function of x and y. Now, the linear approximation, this is what we just got through doing, is nothing more than the equation of the tangent line. Notice we've moved the z naught over to the other side. So this is called the linear approximation for z. So then, if we take this linear approximation for z, we can refer to the quantity x minus x naught as the differential of x, or the change in x. The term is differential. The y minus y naught is the change in y, or differential of y. The z minus z naught is the differential of z, or what is oftentimes called the total differential. So the total differential is what? It's the partial of x times the differential of x plus the partial of y times the differential of y. So all this is saying is you get the total change in z by taking the little bit of change in x and the little bit of change in y and adding those together. Now those differentials are referred to as dx and dy and dz. Now here we see an example where we're given a function of x and y, and we're asked to find the total differential. And we want to use that to approximate the change in z. And so our total differential, using the formula we just came up with, is the partial of x partial of y, the partial of x times the change in x plus the partial of y times the change in y gives us the total change in z.